Military operations typically involve working with partners to resolve rapidly evolving situations where adversaries are adapting their tactics, techniques and procedures, and the behaviour of the civilian population is changing. Thus, military information processing systems need to be able to recognise relationships between sets of individual events which are distributed in time and space in near real time, without generating too many false alarms. Deep learning AI systems are constantly improving their ability to recognise such individual events. Our research enables patterns of events to be recognised where there is insufficient time or data to train a deep learning model. We'll demonstrate two key capabilities. Humans can inject new knowledge or hypotheses about patterns of activity through addition of new rules. AI models can be trained faster, with significantly reduced need for training data and improved detection accuracy compared to pure deep learning approaches. We'll also show how our approach emphasises loose coupling of hybrid kinds of AI systems in an open architecture, and how the resulting applications can run on edge-of-network devices, so are suitable for tactical sensor systems. The research is intended to enable defence to process, in near real time, streaming data from a future Internet of Battlefield Things, and to adopt AI systems which learn and adapt at the pace of the fight. We demonstrate the research in the context of monitoring a rapidly evolving situation in the NATO Anglova urban setting via diverse AI assets processing multimodal sense data with management of situational uncertainty. We focus on 4 AI services, each showcasing particular DAIS research technologies. Firstly, a CCTV processing service owned by Anglovan local law enforcement, located outside a popular nightclub frequented by members of Anglova's Capulet community, detects an active shooter event via deep neural network processing of audio-visual data running on an edge device. To build trust, the service is able to provide multimodal explanations for its outputs with associated uncertainty. Secondly, a social media monitor service owned by the US coalition partner and located in cyberspace detects threats of violence directed against the Capulet community via deep neural network natural language processing on Twitter data. Again, the service can offer appropriate explanations and is equipped to provide uncertainty awareness. The Capulet Plaza Listener service, owned by the UK coalition partner and located in a busy public plaza in the Capulet part of town, processes audio streams via a neurosymbolic AI architecture, able to detect an IED explosion when trained on a relatively small set of training data. Finally, a situation monitor service, owned by the UK coalition partner and located in cyberspace, performs probabilistic logic programming, with rules injected by subject matter experts, to detect that the 3 preceding events constitute a situation of interest, i.e. escalating violence directed against the Capulet population of Anglova.
This is a quick demonstration of the early work towards the Adapting AI Systems to Recognise New Patterns of Distributed Activity demo. This demo shows a situational understanding example based on the collaboration between human and machine agents in a human-agent knowledge fusion environment. The purpose of this environment is a place where human and machine agents can rapidly build and exchange knowledge through tellability, informing new information, or explainability, going deeper into explanations of why information exists or has been added. The separate demo, named Enabling Rapidly Formed Human-Agent Coalition Teams Through Extensible Information Exchange, covers this environment in more detail, should you be interested in the underlying research principles that have informed its construction. The canvas on the left-hand side provides a set of capabilities and services that can be used, customized or extended and shared as needed for each use case. For example, here we have the standard core entity types as well as specific additional extensions to support Coalition Situational Understanding, or CSU. We'll be seeing each of these 4 CSU types created and interconnected as the story progresses. We have the service, which is an AI machine service that has been deployed into this environment, usually in a distributed setting onto the sensors themselves, but they could also be run remotely in cloud infrastructure. We have explanations, which are additional information from the service which provides some form of explanation for any events that are detected. There are uncertainties, which in real systems recognize that all observations and inferences come with uncertainty information, which is essential in terms of any downstream inferences or human assessment. And we have events. These are the events that can be detected by services in this environment, and these are specialized into a number of concrete types based on the capabilities of the services: explosions, violence, shooting, and situations. Finally, there are numerous ways to interact with the information in this environment. For example, if we navigate to the map view, we can see that we have a couple of sensors located on the map, an audio sensor on Capulet Plaza and a CCTV camera here outside the Capulet Club on Anglova Boulevard. And this is within the Anglova city setting within the NATO vignette, and we'll come back to the map later. There are a number of core views, and it's easy to extend with custom views, palettes and AI agents as needed. What we're seeing here are the services that were described in the introduction. We have the Capulet Club CCTV service, the Situation Monitor service, which is generic and trying to make sense of the situation in the city, the Capulet Plaza Listener service, and the Media Monitor service. Two of these services, Capulet Club CCTV and Capulet Plaza Listener, are specifically located based on the sensors they are connected to, whereas the others are not located in a specific geolocation but operate in cyberspace. Okay, so let's see what's happening in Anglova based on the services we have deployed. All the services are running, and we can use this environment to get more information about them and see what's happening as they create events. So we can see here that the Capulet Club CCTV service has observed an active shooter situation in front of a nightclub that is deep into the Capulet controlled area, one of the two leading factions in the city. The explanation for the event contains links to the relevant raw input from the sensor, which in this case is the CCTV video and audio feed. This can be seen on the canvas as the SAVER, Selective Audio-Visual Relevance explanation, which takes the form of an attention highlight video showing the audio and visual relevance of the scene. Full details of the SAVER research can be seen in the corresponding demo named Real-Time Explainable Artificial Intelligence, Time Series and Multimodal Data. This event has been assessed to be likely, some confidence. This is a natural language representation of a subjective logic opinion that distinguishes the amount of belief, disbelief and epistemic uncertainty in the truth of a given proposition. Each event comes with a source uncertainty assessment that can be modified upon ingestion into the platform. The source uncertainty here has been discounted at 80% because the sensor and service are run by the local Anglovan authorities, whereas the coalition user maintaining situational understanding is from the UK. This information is all available in the graph, but is hidden by default to ensure that users are not overwhelmed but can navigate to any relevant information as needed. The analyst has seen this shooting event and would like to upgrade the Situation Monitor service to be particularly focused on any discussion on social media that may indicate increasing unrest, specifically by looking for early indication of violence towards Capulets. This is a technical update and would likely be made by an operator user who has responsibility for maintaining the services, but this environment can also support the input of higher level information from which code such as this can be generated. After reviewing the current configuration, the user decides to extend the rules and link this into the configuration. This could either be done by extending the existing configuration rule or by creating a new additional node as shown here. The rule is now live and has updated the running service accordingly. As time passes, the Media Monitor service, an evidential deep learning equipped asset of the coalition, using a machine learning model able to express epistemic uncertainty when facing unseen data, signals a credible, likely, some confidence threat to Capulets. Due to the earlier rule change, the Situation Monitor service is also triggered, creating a situation based on both the active shooter event and the threats of violence from social media, both of which are targeting the Capulet community. Initially, the uncertainty is likely with low confidence, with the rationale noting that this is computed from component events which are indicated via the is explained by links from the active shooter and threats of violence events. The rules continue to run and the situation will be updated as any new related events are detected, with the certainty being revised accordingly. Finally, an explosion event is detected based on the Capulet Plaza listener service. As with all detected events, a link to the explanation is shown along with the original audio should the analyst wish to assess the event for themselves. This AI service is very confident, generating a very likely certain classification for this event, and since this listener service is run by the UK coalition partner, there is no modification to this certainty. The new explosion event is also linked to the unfolding situation due to the spatio-temporal proximity, and the certainty for the situation is updated accordingly. Mark will now explain some of the scientific details of the Capulet Plaza listener service and how it was able to detect this event. Mark will spend up to 3 minutes talking about some of the science of his area of work.
In this demonstration, we've shown how our research enables patterns of events to be recognised where there is insufficient time or data to train a deep learning AI model. We highlighted two key capabilities. Humans can inject new knowledge or hypotheses about patterns of activity through addition of new rules. AI models can be trained faster, with significantly reduced need for training data and improved detection accuracy compared to pure deep learning approaches. We also highlighted the loose coupling of hybrid types of AI systems in an open architecture and how the resulting applications are able to run on edge-of-network devices, thus suitable for tactical sensor systems. We demonstrated AI services operating in multiple domains, physical and cyber, on a variety of data modalities, with awareness of situational uncertainty. We offer these techniques as a means to enable defence to adopt AI systems, able to learn and adapt at the pace of the fight. Further information on the technologies featured in this demonstration can be found at the links shown on this slide.